In this video, we're going to look at graphing rationals in transformation form. You guys already know the transformation form of a few other parent functions. You know the transformation form of a line in point-slope form, and you know the transformation form of quadratics in terms of vertex form. So if we were to think about the parent rational is y equals 1 over x. When we talk about transformational form, this is going to change a little bit, but it's going to use the same letters that you guys used before when you did transformation form. It is going to be y equals a over x minus h plus k. H is going to show you the horizontal shift. K is going to show you the vertical shift. And A is going to show you the vertical stretch or compression. So we can use the same rules that we used when we did transformation form of the other parent functions in order to graph these using transformations. Now we have to know a little bit more about the parent. So I'm going to graph the parent on the grid that I have here. The parent has not been shifted off the origin. Now when you look at a rational has a couple key features. It has a vertical asymptote. That means a place where the graph does not exist. It sort of veers off at these points. It also has an end behavior asymptote, and in transformation form we can talk about it as a horizontal asymptote. Again, the graph veers off here. It tells you what happens at the extreme values of the graph. Now if we were to plug in some points, like let's say 1, so if x were 1, we would get y equals 1 over 1, which is 1. So that's 1 point. I swear it's on 1, 1. And then let's plug in negative 1. So that would be y equals 1 over negative 1, which is negative 1. So a rational has two branches, and one branch follows those asymptotes like this, and the other branch follows the same asymptotes like that. I swear it's going through that point. We're going to use this as a guide to help us graph the rest of our rationals in transformation form. When we stretch it, it changes it by a magnitude of that much. When we shift it, it shifts the asymptotes around. So let's look at an example to understand what that means. So here we have the rational y equals 1 over x plus 2 plus 3. So the fact that this is a 1, that shows that there's no vertical stretch or compression. This is a plus 2, which means it's a horizontal shift to the left 2, because h is always opposite. And this 3 tells us that I have a vertical shift up 3. So when we actually create our graph, this means that our vertical asymptote is going to be over 2, and our horizontal asymptote, or our end behavior asymptote, is going to be up 3. Since it hasn't been stretched or shifted at all, the shape of the graph remains the same. That means that I still go over 1 up 1, and I get a point on my graph. So that tells me that one branch is up here. And if I go over 1 down 1 from the center where the two asymptotes meet, again I'm going to have a point, so that's my second branch. Yay! We just graphed it. That's all there is to it. Gets a little trickier when we have a different vertical stretch or compression, but really we're just going to be looking at transformations in terms of shifting and stretching. So this one has a negative 1 on top. Now, it hasn't been stretched at all. However, it has been reflected. And this tells me that it has been reflected over the x-axis. Because basically I'm multiplying all of the values by a negative 1. All of the y values by a negative 1. This also shows me that it has a horizontal shift. And remember, it's opposite, so in this case it's over to the right, 1. So let's go ahead and let's graph this. My horizontal shift over 1 shows my new vertical asymptote. And then the fact that it hasn't been shifted up or down means that my end behavior asymptote is still at y equals 0. Now, normally when we graph this, we would go over 1, up 1. However, now that it's reflected, we go over 1, down 1. So our point is down in this bottom quadrant. Same thing for the other side. Normally we go over 1, down 1, but now we're going to go over 1, up 1. So you can see that your branches reflected. They're in the opposite two quadrants. They reflected over the x-axis. Alright, in this case we actually do have a different a value. We have a is equal to 3. This means every time we do anything with the y value, it's going to be tripled, not our usual over 1, up 1. This also tells me that I have a vertical shift down 2. So let's go ahead and let's graph our stuff. If it's a vertical shift down 2, that means my new end behavior asymptote is down here at -2. I haven't shifted it left or right, so the vertical asymptote is still on the y-axis, where x is 0. Now, normally we go over 1, up 1. In this case, we're going to go over 1, up 3, because it has been stretched by 3. A little shortcut that you can remember when you're graphing rationals is that the point, it's going to have a matching point on the other side, or in that branch. That's 3 over and up 1. So that helps me sketch my branch that's been stretched a little bit. It's been stretched by 3. And the same holds for the other side. Normally we go over backwards 1, down 1. In this case, we're going to go backwards 1, down 3. And then again, that pattern still holds that I can use the other 3 to help me graph my branch. So we just went ahead and graphed a rational that has a stretch. We just, instead of went over 1, up 1, we went over 1, up 3. It's the only thing that's different. This one stayed in the correct two quadrants, or the first quadrant and the third quadrant, because of the fact that it wasn't reflected at all. Okay, this one's a little bit of a doozy. Because a is -2, I know that it has a stretch of 2, but it's also been reflected. This also has an h of -1, so that means I need to go left 1. And it has a k of -5, which means I need to go down 5. So let's go ahead and graph these things and see what our new rational looks like. I'm going to go over 1 to the left. That's where my new vertical asymptote is. I'm going to go down 5. That -5 is where my new end behavior asymptote is. Now, normally we go over 1, up 1. But in this case, we're going to go over 1, down 2, because it's been stretched. And then again, that whole, what we saw with the 3 holds. So I can have another point at 2, 1, and that helps me see where my branch is. So again, normally we go backwards 1 and down 1, but we're going to go backwards 1 and up 2 instead because it's been reflected. And then I can do my other point there, over 2. And that shows me where my 2 branches are. You can see that it's been reflected. It's now in the second quadrant and the fourth quadrant. This is secretly exactly the same as the other ones that we did. It just flip-flopped where the k was. If you don't like seeing it like this, you can rewrite it as y equals 1 over x minus 6 plus 4. As long as you keep the signs the same, then you're good. Again, we can see that h is 6, so I'm going to go to the right, 6. And k is 4, so I'm going to go up 4. In this case, a is just 1, and so I don't have to worry about any patterns or stretching that happens, nor do I have to worry about reflecting. So let's go ahead and graph these things. I'm going to go over 6, so my new vertical asymptote is here at 6. It's going to go up 4, so my new end behavior asymptote is up here at 4. No reflections happen, so the normal pattern holds. Over 1, up 1. There's the first branch. Over 1, down 1, and there's the second branch. I know that my graphs aren't like exactly perfect, so my excuse is that my stylus is a little bit big. For rationals, it's really important that you get the gist of the graph, not every single point exact. You just kind of want to know where to look for solutions to that problem. And that's really all there is to graphing rationals in transformation form. It's really not that bad. So I'm just going to do a little recap. The transformation form of rational is y equals a over x minus h plus k. Remember that a tells you the vertical stretch or compression. Usually it's a stretch. And it also tells you that if it's negative, that means that it's been reflected over the x-axis. Then we also have h, and remember h is always opposite, and that shows you the horizontal shift. And then we have k is always the same, and that shows you the vertical shift. One thing that's really cool about algebra is that there's consistency to it. So transformation form of a line versus transformation form of a quadratic versus transformation form of a rational. It's all the same. You're doing the same things. H is the opposite, and you're horizontally shifting. K is the same, and you're vertically shifting. It even holds for conic sections, too, when we have to shift it left and right. That's it. If you want to, I know this was really short. You're used to me going on and on for like 15 slides. If you want to go back and look at them again, I basically did every kind of example that you might see. Now, this is getting you started for more complex graphing, so it's a good idea to make sure you've practiced with transformation form before we move on to the crazy ones that, spoiler alert, also involve factoring.